is a reminder of what some of these inverse trig functions mean. So, let's start with that. Let's see. If I tell you that an angle theta is the inverse sine of some number t, that tells you that two things happen. If an angle theta is the inverse sine of t, then what should the sine of theta be? What was the whole point of the inverse trig functions? Like they're trying to undo trig functions, right? So if this is like what you get when you undo the sine function, then what should sine of theta be?
Is it 1 over t?
No, just t. Just how like ln of a equals x means e to the x equals a. Logs undo exponentials, inverse trig functions undo trig functions. But it also means one more thing. You're only allowed to use certain angles in your outputs for inverse trigonometry, right? In the restricted domain before we inverted. So for an angle to be inverse sine of t, what do you need that angle to be in between? What's the range of inverse sine?
Pi over 2, pi over 2.
Nice. It needs to be in between negative pi over 2 and plus pi over 2. And let's do the same thing for cosine. Theta equals inverse cosine of t should mean cosine of that angle theta is equal to t. And this angle theta needs to be a valid output from inverse cosine. So it needs to be in the range of inverse cosine. And what is that?
0 and pi.
Needs to be between 0 and pi. Nice. So, what did we do with that last time? It's like the last thing we did in the previous discussion is we used that to compute inverse sine of the sine of 27 pi over 5. So that means I needed to find a new angle whose sine was the same as the sine of 27 pi over 5. And that angle had to be in between negative pi over 2 and pi over 2. And so what we wound up with was negative 2 pi over 5. Let's do that again for cosine. Let's try to compute. Let's put it in the spot where the final answer goes. Let's try to compute cosine inverse of cosine of 27 pi over 5, and we'll follow roughly the same algorithm. 27 pi over 5, that's like a big angle. And that like, it has some extra 2 pi's in it. So, step 1, let's throw out the extra 2 pi's. You do that by first trying to see how many multiples of pi there are, by doing like long division or something. So let's start with that. Step 1, do some long division. You divide 27 into 5, you get some amount with a remainder of some amount. And what totals are those?
5 pi, 2 5 pi.
Yeah, cool. 5 pi plus 2 over 5 pi. Because when you do the division, you get 5 with a remainder of 2. Fair enough. And I'm okay blowing through that because like we did exactly that last time. It was the exact same force move. All right, so you take a look at that. Do you have some extra 2 pi's you can throw out? Yeah. You have 2 extra 2 pi's. When you throw those out, what are you left with?
A pi.
You have 1 pi plus an extra 2 pi over 5. And so far, right, super familiar from what happened last time. Because we haven't actually involved cosine in our walk so far. We've used like, this is the same point on the unit circle. This angle is coterminal with the angle we started with. All right, let's go and draw a picture So I think I want two things on this picture. I want, well, the output angle needs to be in the range of inverse cosine. By looking back on the board, what's the range of inverse cosine?
0 to pi.
0 to pi. So it better be in between an angle of 0 and an angle of pi. So let's trace those out. There's an angle of 0. Does the purple show up as different from the black pen at all? Okay. Then let's try green. That look different enough? All right. Right, there are angles between 0 and pi. What quadrants does that trace out? Quadrant 1 and quadrant 2. Ooh, let's also draw an angle of pi plus 2 pi over 5 in baby blue. There's an angle of pi plus a little bit more. Is that a quadrant we're allowed to have our answer live in? No. So like, we actually can't get away with just adding and subtracting more 2 pi's because that'll always leave us in that quadrant. So I need to find a new angle which has the same cosine, so the same x value, but lives in quadrant 1 or quadrant 2. So what should I reflect that thing over?
X.
Yeah, reflection over the x-axis. Do the reflection that changes the y value. So you reflect it over the x-axis. So that new angle, after you do the reflection, that's the angle that I want. Well, if you want to reflect over the x-axis, what does that do to the angle? Subtracting pi over 2 is going to like swap x and y. Sorry, it'll.
You could take pi and subtract 2 pi over 5.
That'll do. Yeah, so let's visualize it this way. I'm going to write something else in this space too. Let's draw this picture again. So instead of thinking of any of these like big picture ideas, there's an angle of pi plus an extra angle of 2 pi over 5. Well, instead of going pi plus 2 pi over 5, let's do pi minus 2 pi over 5. That would do the job, right? Go back by 2 pi over 5. Yeah, nice. That reflects over the x-axis. Oh, cool. So it looks like I'm getting an angle of pi minus 2 pi over 5. And simplify, what is that?
3 pi over 5.
3 pi over 5? Alright, so let's do one sanity check. If we've done all of this geometry correctly, this still has the same x value. 3 pi over 5, is that in between, as a number, is that in between 0 and pi?
Yes.
Cool. Oh, cool. There's the inverse cosine of the cosine of 27 pi over 5. And there were some moving parts there, so let's do one double check. You've got like calculators on you, yeah? Here's what I'll have you do. Make sure you're on radian mode. Get me approximate values for the inverse cosine and cosine of 27 pi over 5. Get me an approximate value of 3 pi over 5. Hopefully they agree. If they don't, then we need to see where something went wrong. What'd you get? Well, not just thumbs up. Tell me the numbers.
1.88.
Do I hear a second for both of those worked out to be about 1.88? Nice. And you actually have more digits, so you're like even more confident than that these are the same. Neato. So I'm also going to use an alternative plan to this, which was a good plan. It was picture-based, and it was actually simpler than what I'm about to do. If you want to reflect over the x-axis, one way of doing that is just making the whole angle negative. It's like, if you reflect up or reflect down, those differ by reflection over the x-axis. So here's like another approach. If you reflect over the x-axis, you will replace theta by negative theta. So that'll get me negative pi minus 2 pi over 5. So that's negative 7 pi over 5. Wait, but is that in between 0 and pi?
I think so.
I mean, it can't be. It's negative. It's like the right point on the unit circle to be in that quadrant. But as a number, it's not between 0 and pi. So, it gets you to the right point on the unit circle, but it's like negative. How would you fix that?
Make it not negative.
Yeah, how do you make it not negative? Well, you can add 2 pi again, right? That preserves cosine. Step 3, if you're not in the right range, then in the last step you might need to add or subtract some more 2 pi's. If you want to take that and make it positive, should you add or subtract?
Add.
Add. How many 2 pi's do you think we should add? Let's start with 1 and see if it's enough. What's negative 7 pi over 5 plus an extra 2 pi? I hear 3 pi over 5? Because right, the 2 pi is going to be 10 pi over 5? Oh, good. It got us to the same place. So there's more than one way to get to the end result of these computations. The point is, if you want to compute inverse sine of a sine of something, inverse cosine and cosine of something, step 1, take advantage of symmetry properties to, like, say you can throw out some 2 pi's. So throw out some 2 pi's. After you do that, ask yourself if you're in the correct quadrant. If you're in the correct quadrant, great. Otherwise, you need to do a reflection and figure out what that reflection does to the angle. After you do that reflection to get it into the right quadrant, ask yourself again, is it in the right range? If you're looking at inverse sine, it needs to be between negative pi over 2 and pi over 2. If it's inverse cosine, it needs to be between 0 and pi. If it's not, then add or subtract an extra 2 pi. Seem like a plan? Nice. There's some homework problems that have you do some things like this, and some that are more complicated than that. As you go through and do them, bring up questions. It's the web work assigned for yesterday, so you know it's due this coming Friday. So maybe have some questions about that for me on Monday. There's one question in particular that you are intended to struggle a bit with. So once you get to that one, you'll probably know the one. Give me some questions. All right. Here's the goal of this section of the notes. 2 things. The first is, we can talk about inverse sine, we can talk about inverse cosine. Do you suppose we can also talk about inverses of the other trig functions? Yeah, great. I'm going to develop inverse tangent. In the book there's a treatment of the other ones, but I think these 3 are the most important ones. So let's get inverse tangent. So I'm going to give the setup here, so I have it on the board. So I'm going to get the same thing. There are going to be 2 conditions. I guess the first one's obvious. Theta equals inverse tangent of t. What should that mean about theta? And say the original trig function. What should the tangent of theta be? Yeah. Trig functions and inverse trig functions are supposed to undo each other. And then this angle theta is going to need to be in between two numbers. And we'll figure out what numbers it'll have to be in between, like right now. So we'll follow the same strategy as we did yesterday for getting inverse trig functions. Let's start with what the graph of tangent looks like. Ooh, do you just remember what the graph of tangent looks like? Ah, okay, well we can remember. So remember, tangent is like the slope of the line from the origin to the point on the circle. So there's an angle of 0. What's the slope of my arm? 0. So what's the tangent of 0? Cool, so I guess there better be a point at 0, 0. And now the angle starts going up. Is my arm's slope positive or negative at this point? Positive. So tangent of a slightly positive number becomes positive. And it keeps going up, keeps going up. Ooh, at a right angle, what's the tangent? What's the slope of a vertical line? Well, it's like a trick question, right? Yeah, undefined or infinity. There's a vertical asymptote. So that happens at a right angle. What's the radian measure of a right angle? Cool. And now let's go negative. There's an angle of 0. I start rotating down. The slope is negative. And I get down to negative a right angle, and the slope is infinite. So there should be another vertical asymptote. Cool, there's that. And let's see what tangent keeps on doing. So there's the right angle, so there's pi over 2. And then you go a little bit past that. Does my arm have positive slope or negative? Negative, right? I'm facing the wrong way to be short, but it should be negative. So the other side of the vertical asymptote is there. Back to an angle of pi, it gets to the 0. And then there's another vertical asymptote, and then it repeats. And let's see, those of you who in the meantime just like busted out your calculator and had that sketchy graph or just graphed it from memory, hopefully that agrees with what you had. Great. Nice. There's the graph of tangent. Remember, the whole point of getting this graph is I want to study the inverse function to this function. Is that function one-to-one? Does it pass the horizontal line test?
No.
No. It fails very badly. If I draw any horizontal line, that horizontal line, well, it's a bad horizontal line, crosses the graph infinitely many times. So, is it one-to-one? No. So, does tangent actually have an inverse function? No, because it's not one-to-one. But, I mean, you know what I'm about to do? I'm going to fix this by taking as much of the graph of tangent as I can while still having it be one-to-one. So, I'm going to start at 0 because 0 is like the simplest thing to start with. And I'm going to go to the right as far as I can before something bad happens. How far to the right can you go before something bad happens? Pi over 2. Cool. Right, people would want to say you can go all the way to pi and still have nothing bad happen. If you saw that much graph, would you say that's one-to-one? Yeah, so you could use that to define inverse tangent, but you shouldn't, because it'd be nicer to have that piece of the graph, right? Cool. So there is the piece of the graph that I will use to invert to get inverse tangent. Is there a restricted domain containing 0 on which tangent is one-to-one? It looks like I can use that. What have I restricted the domain to? Yeah.
Round bracket, negative pi over 2, comma, pi over 2, round bracket.
Nice. Negative pi over 2 to pi over 2, excluding endpoints. Oh, and notice I have to exclude those endpoints. Those endpoints aren't in the domain. Highlight the restricted graph, already done. So, the arctangent function arctan of x, also known as inverse tangent of x, also sometimes known as a tan of x, depending on what computer system you're using, is the inverse function to tangent after its domain has been restricted to negative pi over 2 to pi over 2. And now we can graph inverse tangent, can't we? How do you get the graph of a function, a graph of an inverse function from the graph of the original? Swap the x's and y's. Or if you like, it's reflecting over the line y equals x. Oh, cool. 0, 0, 0, 0. A vertical asymptote at pi over 2 becomes a horizontal asymptote at pi over 2, but it's only on the one side. And a horizontal asymptote on the other side at y equals negative pi over 2. Neato. Feeling good? Let's read some things off of that graph. So what's the domain of inverse tangent? Nah, that's the range. Infinity is involved. There we go. All the real numbers. So the domain of a function is what x values do you see on the graph? Well, you see all the x values on the graph. So the domain is all the real numbers. The range is negative pi over 2 to pi over 2 because those are the y values you see on there. Oh, well now we're going to fill this in. Inverse tangent of x equals theta means tangent of that angle should be whatever that input is. And that angle needs to be in this range. Cool. All right. So let's remind ourselves of some things for all of the trig functions now. Well, the three inverse trig functions we've developed. Oh, maybe I'll ask this too. Could you do the same sort of analysis for inverse secant and inverse cosecant? Oh, and I guess inverse cotangent also. Yeah, great, so you can. We won't really study those in this class, but they're no more complicated than what we've already got. Nice. All right, inverse sine, what is its range? Well, it's also on the board if you look in the right spot.
Negative pi over 2 to pi over 2.
Nice. And that one is inclusive because it's all equal to. What's the domain of inverse sine?
Negative 1 to 1.
Negative 1 to 1. Because right, that should be the same as the range of sine. The most extreme sine can be as negative 1 and 1. Same question for cosine. What's the range of inverse cosine?
0 to pi.
0 to pi? Yeah. And its domain?
Negative 1 to 1.
Cool. And tangent, what is its range? Well, it's also just a few inches above on the piece of paper, right? Well, let's write it again anyway. Negative pi over 2 to pi over 2. And the domain of inverse tangent?
All real numbers.
All real numbers. Or if you like negative infinity to infinity better, do negative infinity to infinity. They mean the same. Nice. I want to also put a unit circle picture of these ranges. So I'll start by drawing myself 3 not terribly big unit circles. All right. Negative pi over 2 to pi over 2. Let's draw that. So there's an angle of negative pi over 2. And then I include things bigger than it until I make it to positive pi over 2. There's the range of sine inverse. And let's just point out, what quadrants did that trace out?
1 and 4.
1 and 4. Or I guess if you list them in the order you saw them, then 4 and 1, but who cares? Well, what if you do the same for cosine? Well, it starts at 0, and then the angle starts going up, and it keeps going up until it makes it to pi. Oh. What quadrants is that?
1 and 2.
1 and 2. Same thing for tangent. So you start at negative pi over 2, but you don't quite include negative pi over 2, so you should have an open circle. And then you start going up until you make it to pi over 2, but you don't quite include pi over 2. So that's again quadrant 1, quadrant 4. Cool. So keep these ideas in mind because they'll be relevant in some computations that we'll do soon. All right. So here's another thing that you can use. You can picture inverse trigonometry as being things involving right triangles. Because let's think about an angle of inverse sine of 6/7. So if theta, let's call that theta. If theta is the inverse sine of 6/7, then what can you tell me about sine of theta? It's 6/7. And let's also ask, it's not 6/4. Let's also ask this, what quadrant should that angle be in?
1 or 4.
It's either 1 or 4,
1.
and it has to be 1. Why 1?
Because 1 is both the values are positive.
Yeah. So it's an inverse sine, so it has to be quadrant 1 or quadrant 4, but 6/7 is positive. Y value has to be positive, that's just quadrant 1. Oh, cool. You can draw a picture of that. There's a little coordinate axis. I'll draw this angle of theta right here. And let's draw a right triangle picture. Sine is supposed to be 6/7. So what sides of that triangle could I label? Hypotenuse and opposite. How should I label them?
7's a hypotenuse. 6 is opposite.
Nice, because sine is opposite over hypotenuse. So let's have the opposite be 7, opposite be 6, hypotenuse be 7. Neato. All right. And now let's remember a few things. So sine inverse of x, that should always be x, as long as you're in the appropriate domain, namely -1 to 1. If you go beyond that, you just get a domain error with inverse sine. If you want cosine of inverse cosine, you will always get x, at least as long as you're in between -1 and 1, so you don't get a domain error. If you want tangent of tangent inverse of x, that will always be x independent of what x you plug in, because the domain of inverse tangent is all real numbers. Cool. So that's just like a nice summary of all the stuff we have right now. What I want to do with my remaining 20-ish minutes, 18 minutes, I'd like to think about functions that are like, well, they're kind of like these, except I've mixed up the trig functions. I'd like to think about things that are like sine of the inverse cosine of x. So let's just try it. So we'll use a blend of thinking about right triangles, thinking about quadrants, and use that to try to compute trig functions. So let's start with one. Let's try to compute the cosine of the inverse sine of -3/5. And on the one hand, right, like you could definitely use a calculator and just get a decimal approximation. I think I don't want to do that. I'd rather see the ideas. So let's start with this. Let's think about inverse sine of -3/5. I should think of that as being an angle. So I should think of sine inverse of -3/5, let's call it theta, is an angle. And what's special about that angle? Yeah.
You know what the sine is -3/5?
Sine of theta is -3/5. And let's also picture the unit circle, -3/5. So there are like 2 points on the unit circle that correspond to a sine of -3/5. What quadrant should the angle that I want be in?
4.
Quadrant 4. Because it has to be quadrant 1 or quadrant 4 because that's the range of inverse sine. And it's negative, so it has to be quadrant 4. And theta in quadrant 4. So let's just summarize. So right now I know sine of theta is -3/5, and theta is in quadrant 4. Let's draw a picture that summarizes that. So it's in quadrant 4, so I should like rotate down to get to it. And let's also draw a right triangle to illustrate it. That's a right triangle. What sides of that triangle can I now label?
Opposite and hypotenuse.
Opposite and hypotenuse. How should I label them?
The opposite will be -3 and the hypotenuse will be 5.
Nice. -3, I guess because it's going down. And the hypotenuse, well, you shouldn't really put a negative on the hypotenuse because like there's not a sense of up or down for the hypotenuse. Oh, nice. And I want to compute cosine of theta. That's right, I want to compute cosine of sine inverse of -3/5. And all that stuff is theta. Ooh. SOHCAHTOA. Cosine is adjacent over hypotenuse. So it looks like I need to know the adjacent side on that right triangle. What is the adjacent side on that right triangle? Yeah, cool. Let's solve for it. So, solving for the adjacent side. Adjacent squared plus -3 squared equals 5 squared. All right, need to solve that for adjacent. That looks easy enough to do. Will the adjacent side wind up being positive or negative in this picture? Positive, because it's in quadrant 4, the x coordinate will be positive. I hear a 4. Do I hear a second for 4? Awesome. Do I hear a call from me to do the algebra? Okay, that's good. How many people just like skipped doing the algebra entirely and said this is a 3-4-5 triangle? Yeah, nice. If you recognize a Pythagorean triple, use it. Oh, cool, so the adjacent side is 4. So cosine, I can use that now. That's adjacent over hypotenuse. So what's the cosine of this angle?
4/5.
Neato. Cool, that feels pretty good. And maybe I'll have you do one thing to now double check. There were some moving parts there. Let's use the fact that we have calculators. Ask the calculator, what is the cosine of the inverse sine of -3/5? Or I guess the cosine of the inverse sine of -0.6 if you like decimals. Yeah, go ahead and give him a nudge. Oh, okay, you're still here. Okay. Okay. Someone was snoring over there. Oh, that was you!
Why you been having me all
Jesus.
I know what you got.
And now you make me swear on the recording. Anyway, what'd you get when you did the computation? Using 4/5? Awesome. 0.8 if you got a decimal. Cool. Here's the next thing I want to get. We can actually just get a canned formula, an algebraic formula for this concatenation of trig function with inverse trig function. And let's try to do exactly that. So let's try to compute cosine of the inverse sine of any unknown variable x. And we'll do it in exactly the same way. I guess I don't know if x is positive or negative, so I won't know exactly what quadrant this angle theta is in. But I will know which two quadrants it could live in. What quadrant will this angle theta live in? 104, because it's an inverse sine. So this theta is in either quadrant 1 or quadrant 4, and the sine will be whatever that number x is. Oh, cool. Well, we can use that now, right? So I guess let's use quadrant 1 or quadrant 4. In quadrant 1 or quadrant 4, is cosine positive or negative? Or undecidable?
Positive.
Positive. Cool. So whatever the answer to this is going to be, it's going to be positive. Maybe it might be equal to 0 because, like, maybe I'm right at the axis. All right. So I know sine of theta is x. Let's think of that as being x over 1. Oh, neat. Can I, like, draw a right triangle again? Yeah, I guess I don't know if it's positive or negative, so I can't, like, know that I'm in the correct quadrant. But that's okay, I've already decided based on the quadrant that I know x has to be positive, cosine has to be positive. So, SOHCAHTOA, sine is opposite over hypotenuse. It looks like I need to know the adjacent side. Oh, what is the adjacent side in this triangle? Oh, I don't know. Should I do the algebra now? Cool. Then I'll stall for a bit. Tell me, how long is the adjacent side? It will depend on x. No, I don't think it'll just be x. Let's see, so what's the, like, right triangle rule that we can use? A squared plus b squared equals c squared. So adjacent squared plus x squared equals 1 squared, which is 1. Now I need to solve that for the adjacent side. So I guess I need to, I hear a
1 minus x squared.
1 minus x squared, because I can subtract x squared. It will be in a square root, because I still have to deal with that squared on the adjacent, right? Oh, cool. So it looks like the adjacent will be the square root of 1 minus x squared. Why not plus or minus?
I was just gonna ask, couldn't you just be, take the square root of it and it could just be 1 minus x?
Ooh, remember though, square root doesn't behave well under subtraction. Like, you can't distribute a square root over a sum or difference. You can distribute it over multiplication, but not over addition and subtraction. Oh, cool. So cosine of inverse sine of x is square root 1 minus x squared. And here's something that's, like, kind of cool. This stuff on the left-hand side, like, it involves lots of trigonometry. So if you, like, undo trigonometry and then redo trigonometry, well, you actually wind up with just, like, an algebraic expression. Like, if I asked you to, like, set that equal to, I don't know, 2/5 and solve for x, you could by just doing algebra. You wouldn't have to do any trigonometry at all. So that's kind of neat. And I think that's worth putting in the formula spot on the previous page. Cosine of the inverse sine of x is always the square root of 1 minus x squared. Feel pretty good? Groovy. Now I should speed up a little bit because I have 7 minutes left on the clock. Do you think we could do the opposite? Like what if I instead asked you to do sine of inverse cosine? Let's see if we could repeat the same reasoning. So this inverse cosine of 5 thirds, same deal, I should think of that as an angle. So theta, I should think of it as an angle, is cosine inverse of 5 over 13. So that means that this is an angle whose cosine is 5 over 13. What quadrant should this angle be in?
1 or 2.
1 or 2? Which one of 1 or 2?
1.
1, because it's positive. Range of inverse cosine is quadrant 1 or quadrant 2. 5 over 13 is positive. It's like, goodness, there-ish. So this angle is in quadrant 1. So the end answer, sine of the inverse cosine of 5 over 13, do I expect the answer to be positive or negative? What's the value of sine in quadrant 1? Positive. In fact, in quadrant 2, it's also positive, isn't it? Okay, so sine of inverse cosine, always positive. Oh, could we like draw a picture like the same right triangle picture now? Yeah. I know the cosine of theta is 5 over 13. So, if there's theta, I could start labeling the sides of this triangle, not drawing to scale. Adjacent side is
5.
hypotenuse is
13.
cool. I guess I need to know the opposite. How many people could tell me the opposite, in fact, without doing any algebra because they like recognize a number? What is it? Like you're at 12. But like, you can also now take a moment and find it. Or should I take the moment and do the algebra to find it? Okay, cool. Yeah, I happen to pick this one by saying let's start with the Pythagorean triple. 5, 12, 13 is a Pythagorean triple, which just means it's 3 integers that fit onto a right triangle. Anyway, so I want to compute the sine of that angle. So what's the sine of that angle?
Opposite over hypotenuse.
Opposite over hypotenuse. And what is the opposite over hypotenuse?
12 over 13.
12 over 13. Oh, cool. Did that feel like exactly the same walk as you did for the other one, for sine of inverse cosine? Yeah, so the formula you'll wind up getting if you actually do this in general will be the same. Sine of the inverse cosine of x is always the same as the square root of 1 minus x squared. I'm going to put that on the previous page before I flip to the next. All right, so I guess that completely resolves the question of what trig function of inverse trig function is as long as you only believe in sine and cosine. But there are like 4 other trig functions that you might use. Let's think about those a little bit. And let's not think very deeply, let's just add tangent into the mix. And I won't try to get like a general formula, not because like we can't, just because I think it's more important to have the ideas than the formulas. Let's try to compute the cosine of the inverse tangent of negative 4 over 5. And we'll follow the same plan. I'm going to start by saying theta is inverse tangent of negative 4 over 5. That means tangent of theta should be negative 4 over 5. Let's also figure out what quadrant this should live in. What quadrant should it live in?
4.
I hear a quadrant 4. Because of inverse tangent, it's either quadrant 1 or quadrant 4. Because of that. Tangent is negative, can't be quadrant 1, must be quadrant 4. So I have an angle. Tangent is negative 4 over 5. And theta is in quadrant 4. Ooh, in quadrant 4, will cosine be positive or negative? Positive. So I expect the answer to be positive at the end. And now, let's draw a triangle. I'll start with my coordinate axes. I want to draw this thing in quadrant 4. And tangent is -4/5. So that's opposite over adjacent. So I guess the opposite's the one that's got to be negative? Oh, cool. And I want to compute cosine? Yeah, I want to compute cosine of theta. Well, cosine of theta is adjacent over hypotenuse. So I guess I need to know the length of the hypotenuse. What's the length of the hypotenuse of this triangle?
The square root of 41?
I hear a square root 41. Do I hear a second for square root 41? Do I hear a call for me to do the wash to get the square root of 41? Cool. I think that even agrees with my memory of what the previous section said, so I'm feeling confident. Oh, is that enough information? We now just know what cosine is? So what's cosine?
5 over square root 41.
5 over square root 41, and before we call it, that should probably be simplified, right? Let's rewrite that so it doesn't have a square root in the denominator.
5 squared 41 over 41.
Nice. Just multiply and divide by root 41. And one last one, because I don't really have the time, but... Oh, could we also have computed sine? Without doing any more walk? If you wanted the sine of tangent inverse of -4/5, well, I guess it would be -4.
5 squared root of 41 equals 41 times 4.
Yeah. Hopefully I at least said 41.
I think you did.
The point is you can also compute sine. And as I start packing up, because I am at time, I'm going to point out extra credit which is not super challenging, but one which I think would be interesting to do. You could do this for any combination of trig function and inverse trig function. Do this walk and get me a formula for sine of the inverse tangent of x, which will depend on the variable x. Do the walk, draw some triangles, come talk to me.
Do you have office hours today?
No, not on Fridays.
Oh, got it. Okay.
Have a weekend. You too.
I wonder if you would have got